So I just record the notes for there and we'll put that. But so that's kind of a thing. We find that difference, and then dividing, we've done this before, right? This stuff on the bottom, that's kind of that standard error about the mean, right? So this is that standard error, we've done that before. Right, that standard error about the mean or something, whatever that, however we phrase that. Where before what we were doing when we found a confidence interval was we would take this value times the z-score, right? If we kind of manipulate this equation, right? This is a denominator. We could take the red stuff times z and then add this part over and we have our other equation back, right? Like we would take whatever we thought and we would add and subtract the z-score times the standard deviation, right? It's the same thing we've been doing, but now we're just finding just the z-score, we're not multiplying by it. So we're not finding a range, we're finding a value, and then we're going to compare that value, right? Whereas before we were finding sort of a spread. So it's pretty much the same thing, just slightly moved around a little, and then we're going to go from there. So most of our stuff today is just looking at examples and using that, okay? Today's example, we're going to work off of proportions. So if we're doing like, hey, a percent of people said yes, a percent of people in this example are enrolled in colleges. Tomorrow we're going to do the same thing, right? Same examples, or not the exact same examples, but same type of thing. But then we're going to do like, hey, what if you have quantitative data, right? What if you have a mean and a standard deviation that way, rather than just a proportion? But, so in here, you know, this is one I think I just pulled from the book. I don't remember where I got that data from, but this might be something, right? They wanted to say, okay, maybe somebody reported, or some news program, whatever, reported, hey, 85.6 of college students are undergrads, right? Do you guys understand the difference between an undergrad student and a grad? I did not when I was your age, which is why I asked. Some people did, some not. So to give you a quick understanding of that, so when you go to college, there are kind of two categories there. So like you guys, kind of like in here, you have your upperclassmen and lowerclassmen, right? You have your high school, junior high. Right, when you go to college, you kind of have your undergraduate, and then you have your graduate students. So undergraduate, that usually takes 4 years, right? That's your kind of general thought of stuff. A lot of people take 4 years to do that. You graduate, you get a diploma. Yeah, so I did that, went to college for 4 years, and I got my diploma in, so I got two, actually. I got one for teaching math and then one for pure mathematics, right? So I got two on that one. And then after you get that diploma, after you do that, you could continue, and then you're called a graduate student, and that's where you might get what's called a master's, which usually is about 2 years, which that's what I did. I went back and got a master's so that I could teach some of the college stuff and have a little more information on that. But you could keep going. Sometimes people go for 4 more years after they get that, and that's usually like a doctorate is what you call that one. But anybody who goes beyond that first 4 years is sometimes called a graduate student. Does that make sense on there? But that's it. So saying most people that go to college are undergrads, right? Because like they get their 4 and they're like, I'm done. I'm not going on anymore, which would make sense, right? So they wanted to see here, in Oregon, is that different than what they reported, right? Is Oregon different, right? Because that's what they're saying. Is this different? Is my group, the group in Oregon, different than what this other national average said? So my first thing that I would do, and you don't have to do this every time, but I'm going to do this here just for emphasis, right? I'd start out, step 1, I'm going to write down my hypotheses. The hypothesis is that the proportion, I'm going to use P instead of mu because it's a proportion, it's a percentage. I'm going to say, hey, the proportion is just, hey, that's what you said it was. Proportion's 85.6. Maybe that's the same here in Oregon. I don't know. Right? My alternate is what I'm going to check. It's like, well, hey, I think maybe this is not 85.6, right? I don't think it's the same. I think it's different. And we put that in. So that's kind of step 1, setting that up. And step 2 is to kind of draw out our critical regions, right? Here, you're using an alpha of 5%. That means that's in the tails. and we're not equal to, which means I could go either direction. I could go smaller or bigger, so I have to split that 5% into both sides. So I'm going to split that 5% into both sides. And this is what we've done before, right? Nothing new here, right? Kind of the same as finding a 95% confidence interval. Now what I want to do is I want to look up and find my critical z-score, right? So I'd look up here and say, all right, well, what's my z-score for that? Which that we've been doing, right? That would be on our sheet, right? Our kind of t-score or z-score sheet, whichever one you want to use. I'm going to use the t-score sheet because it is a little bit faster, right? So I would go to this page here. I'd say, all right, I have, 25% in one tail, 5% is in both tails. And we want the z-score for that. So go down here and grab, okay, there's 1.96, right? Those first 3 steps, this stuff that I'm doing right now, we could do all of this setup without having done any sampling, right? We don't have to go and check any sampling for these first 3 parts, right? I don't need any other information. I haven't gone and grabbed a sample, and in fact, for a good statistical study, this part would be done before going and gathering the data. We would set up, here's my sort of estimate, here's what I think is going to happen, and here's my threshold, right? You would set that up first, and again, that is to get away from sort of the ethical dilemma of like, well, what if I gather the data and go, oh, I don't think it's quite going to fit. I'm going to go back and change this. Maybe I'll say, hey, what if we make this 7%? Okay, so it changes your thresholds a little bit so that you can then change your results. We don't want to do that. So we set that up first, and then we test it, right? So now we go to our actual step 4, right? We're going to say, okay, now I'll go to step 4. I'm actually going to test my data. So I'd look at my data and say, okay, I'm going to need, and this stuff is just proportions, so I'm going to need, what do we know? So in this case, the proportion from my sample, right, that I went and gathered, is 420 out of 500, right? So we could divide that out and say, hey, what's that as a percentage? I believe, because it's out of 500, so I think that's right. Should just be able to double it and be out of 1,000. So I think that's 84% of the enrolled kids are in undergrad, or at least the ones that we asked. Okay, so far. Okay, so that's kind of that part. And then I need to get a z-score from this value. Okay, and this is my test value. So I'm going to write that as my z-test, or however you want to label that, so that I don't mix it up with this green one. So the green one is on its own, it's separate. I'm finding this is from my data. Okay? And how we do that, we can follow through that formula that's on the sheet before. The numerator is we're just going to find the difference, right? We're going to look at what's the difference between what we found, our 84%, and what the claim is, 85.6%. Okay, that numerator is just, hey, what's the difference between those two things? So we look at that and say, all right, what is the difference between my value and the claim, right? How far apart is the one that I found and the other one? There's probably going to be a difference, right? Very rarely, if you take even 2 different samples from the same group, you're very rarely going to get exactly the same thing every time. But the idea of this test here is 1016, so 1.6%. And you're very rarely going to get the same thing, but the idea of statistics is saying, is that difference large enough to account for any randomness, right? And that's why we run this test, because there is random variation. Is that random variation, is the difference due to just randomness, or is it due to an actual large difference? And then on the denominator here, right, I'm just reading along on our thing here, putting that in red. So it just says the square root the P and Q that we're gonna use are from the claim, right? And so that's kind of different. So if you wanna look in there, that's from the population from the claim, not from my sample. The only part that we use from the sample is the P hat and then the N on the bottom, how many people did we sample. So on here, I would take the proportion, p-value, which is 0.856 times Q, which how do we find Q then? How do we find Q? Complement, right? 1 minus this. It's whatever combines with this to make 100, right? So I think that should be 0.144, right? Put that one in there. And then I would divide this by N, which is how many people we asked, which if I look back was 500. That's how many people were in my study or in my group. So I'm going to put 500. And then once I got this set up and I take the time to write that down, then I could type this in my calculator. And depending upon your calculator, all right, calculator that I use would look kind of like this. I'd want to make sure to put a parenthesis there, right? If it doesn't put a parenthesis, you'd want to make sure to do that. That would kind of look like if you put that in your calculator, right? You could add more parentheses if you want, but since this stuff in the square root down here, stuff in the square root, like, is already in parentheses and it's all multiplying and dividing, we don't need to worry too much about order of operation there. So, 5 by square root, 0.856. Let's check here. Here. That's about what I got. 1.019. Okay, on there. Everybody able to get that one or work out okay?
No.
Kara still got some. Alright.
Oops.
Got the right idea there. Just pop that on here. So that one's far. But, so we got 1.019, right? That's our test z-score from our sample. That's what we have. And so now what we need to do is interpret that, right? So how do we compare that then? And that I think I put a little bit on here. So we have 2 ways to interpret it. I like to use the critical value method, or you can use what's called the p-value method. They're both the exact same. It doesn't matter which one you use. A lot of more, like if you end up going on or you have to take other ones, a lot of things will use the p-value method more so, and I don't know why. I don't know, it's just kind of the way that a lot of them do. I like the critical value method more. It's just the way my brain works. So essentially what the critical value method is saying is we're going to take a look at that picture that we put before, right? We said our critical values were this, right? We had 2.5% on either side, right? Does that make sense there? This is what we drew before. I'm just kind of redrawing it, right? We had that there. And then we found a test value. The test value was 1.019, right? This was our test value. And so the critical value idea is what we're going to do is take this value and we've got to put it or place it here and see where should it land, right? Remembering zero's in the middle. So if I place this in here, that should be somewhere over here, right? And the question is, does this test value that I have, does that land in the critical region? Does it land in the green area? If it does land in the green area, then we have enough evidence to say, hey, yeah, this, like, ours is different than what you said, right? Like we have enough evidence to say, hey, this isn't just random chance. It's probably a difference. But ours does not, right? It should land about there. We do not land in the critical region. So in here we would say there is not enough evidence to say that, well, ours is really any different than what the other people said, right? Technically, yes. 84% is different than 85.6. Absolutely it is. But our evidence is not strong enough to say that this difference of 1.6% isn't due to just random chance or however we set up the thing, right? Maybe if we ask more people, maybe it would end up being that. We can't know for sure. Maybe it is different, I don't know, but we don't have enough evidence to really say that it's outside of just random chance. We don't know, right? It's not strong enough evidence, at least based on our setup. Does that make sense there? Yes, there's not enough. The other way, the p-value method, which is the exact same thing, right? The p-value method, the advantage is that we don't actually use the critical z-score at all, right? So that's kind of, I think, the advantage to it. You just take whatever percentage is in here, right? We take that, and what we do is we look up, we find on our table, we find the probability that something would be less than 1.019, or I guess 1.02, because the way we look up our table is we go there. So this we've done before, right? We go on our z-score table. So I would go to, which I have to pull up here. And this is why I don't like this one as much, because if I can avoid using this table, sometimes I try to. I mean, it's not super difficult. Just I find this table easier to look stuff up on, which is why I like using the critical value method. But this one works just fine too. So here what we would do is we'd take our score, right, which was 1.019. Now I have to be a little careful, right? Or yeah, 1.19, which I guess I would have to round because I can only look up 2 decimal places. But I got to be a little careful because most of the time, and I did this earlier too when I was double checking stuff yesterday, I looked up 1.02 and I looked it up on this side, right? Which after I looked at it, I was like, oh wait, I can't do that because I would look here, and that's where it is, right? There's the 1.02. You go, oops, that's not going to work very well because that tells me this large portion, right? That tells me all this large space. So that's not what I want. I want the percentage that is in the small tail, right? We always want to look at the small tail. So actually I need to look up negative 1.02, which is somewhere in here, and 1.02, there's that one. Okay? So if I look that up, it says I have about 15.39%, or 0.1539. So I'd go back to my stuff here. Let's see on here. Go back to this stuff, and I'd put that down. I got 0.15, whatever it was, 9 something. 3 maybe it was. No, 3.9. Oh man. Switch them. Okay. But the idea here, what we want to look for in the p-value method is this percentage that I looked up smaller than this one? Right? Is it smaller? Because if it's smaller, that would mean it would fit inside. The only way to fit inside the green region is to have percentages that are small. If the percentage is bigger, then it's outside of that green region, right? That's the essential idea. So on here, we can compare this and say, oh, no, it's not. This is bigger than my sort of alpha value in essence, right? So there's not enough evidence to suggest that this is different than just random chance. Does that make sense on there? And I don't care which way you use. I think some of the questions in the homework, I was kind of grabbing some of them, and we'll do some of those examples today. We'll say, use this method, use the critical value, use the p-value. I don't care. Use either one. Whichever one makes more sense to you, whichever one you want to use is fine, right? You can use either one of these. It doesn't matter. Like I said, I like to use this one, the critical value method. For some reason, it makes more sense in my brain. If I'm bigger, then it means I'm outside, I'm farther away, I'm far enough away. Whereas this one, my brain has to do a switch where the percentage should be smaller because I'm pushing farther away. So for me, the p-value method it takes a second for my brain to switch and actually check that. So it's whichever one you want to do. Does that make sense there? Cool. And then how we would interpret that, or kind of the technical way that we would say this, and you don't have to do this every time, but I'm just putting this here, we'd say, okay, we would state what we use, using an alpha of 5%. We want to state that and then you'd state what happened. Do we have enough evidence or not? In this case, we do not, right? Because it wasn't far enough away. We do not have enough evidence to. The kind of technical way to say that is we do not have enough evidence to reject the null, right? It's not saying that that person was correct, right? I'm not saying that the average is 85.6%. Just saying I don't have enough evidence to say that it's not, right? It seems like splitting hairs, but it is kind of careful on that, right? Think about yesterday to the courtroom area, right? If you're saying somebody, what does the jury always say when they come back? If they might say, we find, if they don't reject null, they say we find them not guilty, right? That's the way they phrase that. They're not saying that the person is innocent, right? They didn't prove that they're innocent, they just didn't have enough evidence to say that they're guilty, right? And that's kind of that phrasing. Same thing. We don't have enough evidence to reject the null that the average or the percent, oh boy, there's probably an hour in there, is different than 85.6%. My handwriting's super great today, right? So, but it's just saying, I don't have enough evidence to reject that null that it's any different than what you said it was, right? If we did have enough, then we say, oh, we do have enough evidence to reject the null, and it's probably different than what you said it was, right? It doesn't mean that my sample is the correct value, it's just saying yours is probably wrong, right? You're probably not correct. Make sense on there? Doing okay, Ish? Okay, so kind of walk through that one a little bit, right? It takes a little while to set it up, but not too bad. So the rest of the stuff here we're doing, we're just going to set up a few examples and kind of work through those, right? Kind of how do we do that stuff? Hopefully going through that. Okay on there? Okay, do you want me to work through one more with you and then try on your own?
We should
Try it a little bit.
Yeah.
Kind of start on it some. So what I want you to do first on this one is to at least set up your critical scores, right? What are your critical scores going to be on this one? Okay. It's different. You're not going to have the same z-score on this one as you did on the last one, right? So how is this different?
Minus the z-score.
Isn't that?
So on this one
No,
here,
wait.
right? So for the setup, are we okay on that part?
Yeah.
Setup's okay, the green stuff. So the next question is, how do we find p-hat? Or in general, what is p-hat? What does that tell us? in general. What does that mean? It's the percent from our sample, right? So in other words, it's the percentage that this particular dentist found,
Oh,
right?
didn't we
So what
divide
percentage did he find?
65?
65.9, right? We don't actually have to divide anything, it's just told to us,
Oh.
right? It's already pre-calculated. The last one, we had to figure it out and divide it. This one, it's like, oh, you already did it. Okay, great.
If
So I'll
we
just-
had to figure it out though, and they didn't tell us, what would we do?
We'd have to do like we did on the last one, so we're gonna go back to that.
2,000 by 60.
Yes, like this one we had to take 420 divided by 50 because it wasn't already done. We would take, in this one, you know, whatever it is, divided by 2,000 to
Okay.
get that percentage, right? But he already pre-did that, so great, I have it, right? And then we can find our z-test value, right? And what we do for that is we find the difference between what the claim is and what we found. What's the difference between the claim and the find? Again, pretty low in this case. They're fairly close together. It's 1.9%. Change it to a decimal, but that's how far apart those are, right? Still pretty close together. Maybe this time though, but he asked 2,000 people, right? Maybe that reduces that random chance. This one might actually work out, but we gotta check. So I take this, say, well, 64 compared to 36. He has 2,000 people, right? There's my setup. Plug it in, see what we can get.
Where'd you get the 0.36?
So the 0.36, I'm just gonna jot this down here before okay. In here, I'm going back to, and always can go back to this little formula here, right? Top stuff, we found the difference, right? So we got that 1.9%. And now I'm doing the red part. It says take P times Q. And that's the claim, from the claim, right? Claim said the percent of people is 64%. Q is just
Oh,
the opposite.
yeah.
So I just said, well, that's
Yeah.
36% of people don't get that claim. And then N is 2,000.
Okay.
So yep, I'm just going back to that formula and filling that one. Okay? Okay on that one?
So then we have to find where 1.77 would be on the graph.
Correct. And now we can go to compare. So we've done all the work, right? So we did step 1, that's in green. We did step 4, which is kind of the blue area over here. We're calculating what our value is. Now step 5 is to take and compare that. Where does 1.77 land?
And
My
the
great picture.
critical.
It lands in this critical zone, right? Lands there. So what we would say is, hey,
Oh, I did 200, not 2,000. There we go.
yeah, we have enough evidence to reject the null. Right, have enough evidence to reject the null. Or another way to phrase it might be, I have enough evidence to say that, you know, this group in Portland, right? This group in Portland has a higher average than the rest, right? Is it exactly 65.9%? I don't know, right? So I only asked 2,000 people. I'm gonna guess there's more than 2,000 people in Portland. But the average in Portland is probably higher than 64%, right? The average there is likely higher. And again, alpha being 5%, remember, that's a 5% chance that we have that type 1 error. In other words, maybe this is a false positive, right? Maybe I think that I'm right, I think it's higher, I'm pretty sure it is, that's what my test says, I'm positive that it's higher, but maybe it's not, right? I have a 5% chance that I have a false positive here, right? But, you know, is that enough, right? And that's, anytime we do this test, there is always a chance that you have a false positive, right? It's just how do you adjust that? Because if you were to adjust this, right, maybe somebody said, well, I don't want it to be 5%, I'm gonna move this out farther, maybe make it 2% or 1%. Maybe then it doesn't fit. But that means then that you have a higher chance that you have a false negative, right? Maybe you say, well, I don't think it's higher, but in fact it is, right? So there's always that balance, right? And we're not, again, not going into all that part, just want you to be aware of it. We're just gonna say, well, here's what it is, but it is good to have that in the back of our minds. But other than that, any questions on like the math, the calculation
We'll do
portion?
another one.
Yep, absolutely, that's what we're gonna do. But any questions on this one, on how we found those things? So just kind of working through those steps. And like for me as well, a lot of times, especially when I'm working on the homework or just kind of doing some examples and practicing, I might skip step one because I kind of get used to it, right? This is what we're doing, we're just testing that it's higher, right? So I don't always write down number one, even though I should, but I'm practicing it. So I often just jump to step two, just draw it out and find the critical thing, okay? But no other major questions there? Okay. So then on the back of your notes, what I did is I just went and grabbed some of the questions from the homework, right? And if we look at those ones, so I just kind of grabbed one. I think this was number 16. This one doesn't have as much calculation. It's just kind of looking at this idea. So it said, hey, it's a two-tailed test. Somebody went and did all the math already, right? They did all those steps, and this is their test, right? This is their test value. They said they wanted to test this using a 1% level of significance. In other words, that's their alpha. And they're doing a two-tailed test. So if I'm going to check this, right, I have two ways to do that, right? I have two ways to do that. Number one, and this is my preferred way, just because for me it's quicker, I'm just going to draw that out. I need to do two tails. It needs to total to 1%. So that means there's 0.5% in either tail, right? Just one side, there's 0.5%. And so then I would go and say, well, what's my critical z-score then? I would go here, say, all right, let's find my critical z-score for that, right? Which I think is 2.576. Right, if I look that up, yep. There's my 0.5% in there, 1% in both tails together. So my z-score, my critical, is 2.576. That's what I'm gonna look at. Okay, there? So that would be mine. I'd say my z crit is 2.576. And then I can compare. So what conclusion do we come to on this one? What do you think? So Kara, I'm gonna pick on Kara to see if she's still awake, because I can't tell you. Your glasses. Yeah, I figured you were. I was just checking, right? You said it earlier. I wasn't doing. So this is our test value, 2.153 compared to 2.576. If I'm gonna put this somewhere, it's 2.153. Is it gonna land in the green region or not? Not. It's gonna be on this side, right? It's gonna be to the left, just a bit, right? I don't know exactly how much, but we got the idea. So what would we say on here? How would we phrase this?
We reject.
We do not reject, right? If we land out here in the green region, then we can say, have enough evidence to say that the other person's claim is not correct. I would reject their claim. I'd say, no, I think you're wrong because I'm farther away. This says I'm not really that far away. Right? I'm not far enough away. We would not be able to reject the null. Okay, we can't do that. The other three here we can actually eliminate. We never really accept the null. It's kind of mentioned that. We never, even if like this way, I'm just saying, I'm not saying you're right. I'm not accepting your answer. I'm just saying I don't have enough evidence to say you're wrong, right? It's kind of a particular way to say that, but I'm not actually, never actually would say that they're right. That's kind of the statistical way to do that. I'm not saying you're right. I just don't have enough evidence to say that you're wrong. And then the thing that we are looking at, our kind of claim, our test, our alternate, we don't actually know if our alternate is correct, it's just used as evidence to reject somebody else's claim. That's kind of how we set that up. Does that make sense there? So really the only two choices are A and B. You either reject the null or you don't reject the null. In this case, we do not have enough evidence to do that. Okay on that part? Okay? All right, so what I want you guys to look at is number 17, right? Same type of thing. What would our decision be? Again, on here, our decision is really A or B. You can either reject or not. These other ones are not, they're just kind of put there because that's what some people would say, but that's not a statistically correct thing to say. It's either A or B. We either reject or we don't. How do we go from here?
How do I find the number on my chart?
Yeah, so how do we do that one, right? So it depends on how you're doing this one, okay? So I set it up to do sort of the p-value method, but you can do the critical value method as well. So how we do the critical value method, right, is we're going to draw a picture, right? At a 5% level of significance, but this is only left. So all 5%, I don't care about the right-hand side, all 5% is on the one side, correct? So when you go to look that up on your table, right, I look across the top, and let's see, we have one tail with 5% of the stuff in that one tail. Does that make sense? That's how I looked that up. Okay, there?
Yeah.
And then we just scroll all the way to the bottom. I want to check what's the z-score that I would need for that. 1.645. Okay. 1.645 would be that one. Okay, there? Okay. And you could check the others, right? If I put the other tail in, it would total 10%. 90% would be in the middle, right? But that's all going to lead to 1.645. So this would be our z critical, 1.645. Technically negative, I suppose, because it's on the left, right? But not too bad. So, do we reject it or not? No? Yes? So how do we check? Is this 1.99? If I were to put this on the graph over here somewhere, is it going to land in the green region or not?
No. What? Oh.
Right? It is going to land in there because it's negative numbers, right? We're looking to the left.
Oh, I see.
1.645 is here. 1.99 would be to the left of that. It would land in the green region, right? Land in the critical zone, meaning that this evidence is strong enough to say, hey, that original thing somebody said, it's probably not correct. I have strong evidence to say that you are not right. I'm going to reject your answer. I don't think you're right. Don't think you're right. My evidence shows otherwise. Okay, there? And this, again, this bottom one here, this is the way I prefer to think about it, because I can visualize that. The other way, and I just kind of wrote this down here to kind of show you guys that one. This one I looked up on the other table. I said, hey, I have a z-score. I can look that up on my probability table, which is not this one, but over here. So I just looked up 1.99 negative, and that told me it's a little bigger than 2%, 2.33%. And then I'm just going to compare that, this percentage, to the alpha value, which was 5%. And that percentage is smaller than the other one, which means it would land in the critical zone, meaning I would still reject that, right? So you could use either. You can either compare the percents or you can compare the z-scores, right? It's just sort of flip-flop. When you compare percentages, you want it to be smaller. That would reject. When you're comparing z-scores, you want it to be bigger. That would reject that. Kind of making sense there? Not rejecting and other stuff. Okay. Yep. This one's got a lot of stuff in here, right? On these ones, this one I was glancing through. We can read over this thing too, and I was like, okay, this one here does not have any calculation in it. At first I read through, I was like, because I was grabbing it, I was like, okay, we'll do an example here. It's like, oh, there's actually no calculation after I reread it. Because on here it's just talking about consumer fraud and identity theft. Okay? So 23% of complaints in 2007 was for identity theft, right? The FTC was saying, hey, 23% of people that call in say, hey, somebody stole my identity. Okay? Alaska had their own thing, 321 out of 1432. Is this evidence enough? So we could run the whole test, right? We could run the whole test, the whole thing. But that's not quite what this is asking. This is saying, okay, maybe we find this, maybe we reject the null, maybe we say, hey, maybe Alaska does have more identity theft than the rest of the country, right? Maybe that is. But what would that mean? What would a type 1 error, in other words, a false positive, what would that mean in this case? Okay. What would that mean in this case? So a false positive means I think that I am correct, right? That I rejected this. I would think that I am correct. That's this part. That's the positive. Okay? I think that it's actually less than 23%. Right? That's the positive part. Okay? I think that. But a type 1 error is saying, okay, you think you're right, but in reality, you're actually not, because of however you set up your sample, maybe just by random chance, you thought you were right, but that's not true. So as I read through here, I would believe that it's less than, right? So I'm going to eliminate B and C, or B and D, excuse me, because that's saying more than, right? I believe it's less than, that's my positive part. But in reality, there really was more than that, right? Yeah, that's the identity theft. Oh, sorry, that, right? That's this one here. Yeah, so option C is a type 1 error. I think I'm right. I think my alternate hypothesis is correct. It turns out it was not. That is a type 1 error. Okay, on there, it's a type 1. If we switch that, the type 2 error is saying, oh, I think I'm not right, but I actually am. Right? That would be the switch. That would be the type 1. Okay? Or type 2 error, sorry, false negative. But that is kind of your false positive. I think I'm right, but I'm actually not. Okay? That's a false positive. Okay? And then just think about those errors as well. Right? Just trying to wrap your head around that. So I grabbed this one too. So what would be a type 1 and a type 2 error with a sort of vaccine, right? I grabbed this one. So hypothesis, whatever that might be, what would be a type 1 error? How might we say that? Type 1, in other words, a false positive. How would we phrase that? A false positive. I think you're right. And I think I'm right. Meaning, if it's a vaccine, if the vaccine is right, what is it doing? It's working, right? So I think it works. The vaccine works. But what? It doesn't. Okay? that's kind of our positive. I am positive that it works. But in reality, it does not, right? That's the false portion. That's a false positive. Okay? A type 2 error is also called a false negative. Okay? So how would we phrase that? Yeah, right? I don't think it works. My thought is negative, right? The negative portion is that it doesn't work, right? Vaccine does not work. But the false part of that is saying, oh, it actually does. And it's a false negative, the type 2 error. Okay, I'm there. Just kind of getting around that kind of phrase in general, right? These would be things like, we're not doing calculations, but it's good to know, right? It's good to know, especially as you guys get older, you gotta go on your own, maybe you gotta get checkups or things like that. Understanding the difference between a false positive and a false negative and what's possible when, you know, you might go in for a test or something like that, you know, some kind of medical exam. These phrases are good to know what they mean, right? A false positive means that it worked, that they thought you had something, right? They thought, and that can get confusing in the medical field as well, which is why I will put this question on here, right? So like a false positive, if you go to the doctor's office, would mean they think you are sick. They're positive that you are sick, but you are not, right? Or that you have something, right? That something's wrong, but it's not. A false negative would be they don't think something is wrong, but in reality it is. And in the medical field, a false negative is arguably worse, right? Because you don't know that something's actually wrong. You're going about it, you're thinking, oh, that's fine. And like I said, in class, we're not focusing as much on this type 2. We're using the alpha value. We're looking at type 1 more so, but we go there. All right. Last couple examples, right? These are the ones we were just doing, right? Things there. So we're gonna test this, okay? 1% significance level, and we test this one out. Okay, so this is the example stuff we were just doing. So we'll let you guys kind of set that up. I see, okay. What do we come up with? Is this different or is it not?
I mean, it's a string.
So, setup okay?
Yeah.
Okay. What's our next thing that we would do? Here's the setup, right? That's what we're gonna carry. I guess I didn't get the critical value. I think we had that from before though. It was on one of these back here. I don't remember which one. Somewhere back here. Anyway, what is it, 2.5 something? 576?
Yeah. Where was that?
Where was that one? So this one, I think because we had done it before, that's why I knew where it was. It was on one of our previous questions. So I was looking at this one, yeah, because you have 0.5% on either side. Critical value is 257. And we got that from the kind of our T table here, right? We went to the 0.5% mark, which I know I got a lot of writing on here now. We go to this 0.5% mark one, and go all the way down to the bottom. Okay, there. That's where I pulled that one from. But yeah, we answered that one before, so 2.576. So that's kind of our critical one. Okay. And then how do we set up the actual calculation part? What do we need to find? Baby hat.
That would be 333 divided by 149, right?
Other way around, but correct.
Oh.
Yep. Because smaller number, right? So 149 on a 333, which I find it easier since the other one's a percentage. Actually, type it out. Right. Anyway. Oh boy. And alright, so that percentage. So then we can find our z-score, right? How do we find our z-score on that? 48%. What's the difference? All three-ish, right? 9.4 is like 3 point, or well, let's put our 0 in front of it too, I suppose. Change it to a decimal, right? So it's like 3.26%. That's how far apart these two are. Right? Good there. Now we would divide by. Now just following through that formula that we have on the front. We have our percentage. I think it's 48% have natural gas, which means 52% do not. And in this one we asked 333 people. And then we would get our z-score. Plug it in and see what we got.
I did not get that.
Ah, did you know that? This is just the denominator?
Go ahead.
You gotta do the difference between these two, which is this. So we got 0.036 divided by this thing. The difference gets divided by this square root. And that's our z-score. Which, oops, I still typed it in wrong, right? So hit your second, and then this delete button, hit that, that'll turn it into an insert, so we can hit 2, we'll just push everything into underneath the insert, because I forgot to put the 2 in there. That should work. Okay there? See, you did that right, you just have the bottom on there. So about 1.19. Johnson, what's this mean? Do we reject or not?
We. Okay, wait 1 sec. I need to look up here.
Okay.
We don't reject?
Do not reject, because this value, is it large enough to reach into the green region, into the critical region? It's not, right? It'd have to be in here somewhere. So we do not reject. So there's not enough evidence. There is a difference of 3%, but it's not enough to be accountable for random chance. And that, very likely is he only has 333 people. Maybe just by random chance it's different. Okay, there? All right. And then we'll do one last one, right? Same type of thing. See, is Oregon different than the national average? Is it different? Is there enough evidence to say so? Okay. What'd you find there, Gracie?
I got the answer, I think.
Yeah, which one? Rejected or not?
No.
Not? Okay. So yeah, the z-score is small, but we'll see.
Wait. Yeah.
4, so what's that? 4, almost 4. So 3.9. That's the difference there. Divided by square root. not actually bigger. So that red value, the one that we have, is not bigger, which means we cannot or do not reject the null hypothesis, which write out the word or put that H0, meaning, I don't know. Doesn't seem to be different than that. I don't know really actually if it is, but I don't have enough evidence to say that it's any different than 40.1%. Don't have that. Does that make sense there? Okie dokie. Right? So not too bad, it's just that computation and then our interpretation, we compare that. So not a whole lot that's hugely different on there, but